Blemings Labs. I'm your MC for today, Pia Andrews, and it is my absolute pleasure to introduce our first speaker for the day, Keith Packard. Keith has been developing free software since 1986, working on the X Windows system, Linux, amateur rocketry, and educational robotics. He's currently a principal engineer at SiFive, working at the RISC-V system software, including Linux, Uboot, QEMU, Zephyr, and GCC. Keith has taught computer programming for students aged 10 to 17 using Lego robotics for over 15 years and has started the SNEC language project to use in that work. He received a Usenix Lifetime Achievement Award in 1999, an O'Reilly Open Source Award in 2011, and sits on the Xorg Foundation board. Keith uses he, him, and his pronouns and is one of my favorite people in the linux.conf.au universe. So with no further ado, I'll hand over to Keith.
Thank you so much, Pia. It's such an honor to be introduced by such an amazing luminary in the Australia Linux space. I'm glad to be here. The last time I gave a presentation was also in Australia, although I was actually in Australia last. So a little hardware project we're doing at SiFive called the HiFive Unmatched, which is a follow-on to the HiFive Unleashed board that we did a year and a half, 2 years ago. Sorry for the poor audio quality. I have a headset, and if you're not sending audio to the headset, it doesn't receive audio from the headset. And so I've switched to the internal microphone, which means the audio quality will be okay. Let's get on to the next slide here. Okay, what is the HiFive Unmatched? The HiFive Unmatched is we're trying to make a really functional PC based on the RISC-V processor. And from my perspective, a real PC is something that goes into a regular PC box. So in this case, it's a mini ITX form factor. It's got to have a real PC peripherals, USB, Ethernet, and probably most importantly for a device that doesn't have integrated graphics, a PCIe slot. And so the new FU740 processor has 8x PCIe. And so we're able to put in all the usual PCI peripherals. And indeed, you can see one X16 slot for a GPU, and then a couple of M.2 slots, one for Wi-Fi little one, and the big one here for an NVMe drive. And so it's a really functional, desktop PC. That's the goal. Here's a block diagram of the hardware. You probably can't see it all that closely. The big pieces here are the FU740C000 processor, which is the chip designed at SiFive. And it's got all the usual collection of peripherals. It's got a collection of PCIe stuff with USB hanging off of that. And then it's got a I've got a little audio issue going on here today, of course. In any case, that's probably enough about what's going on with the block diagram here. I can go and actually show you the new processor chip. It looks very much like the FU540 that was on the Unleashed board. We had it made in Taiwan. We got samples back. Okay. Sorry, more adventures. So this is what my actual desktop setup looks like. I've got an RX 580 graphics card plugged into the board. I'm using an HDMI capture device, so you're going to be able to actually see what this computer can do. There's USB keyboard and mouse, and you can see that closed cell form custom vibration isolation system. There are so many fans in the GPU and on the board that if I have it on the table without that, it resonates my desk and makes quite the sound. Thank you, Pia, for letting me know that the audio is still working. It's very helpful. And so that's how I actually installed it in my lab right here. The goal, of course, is to be able to take the same board and put it into a regular PC case. You can see it's using a regular PC power supply with the ATX connector. You can see the CPU and the PCIe bridge sitting there on the board. Okay, so this is a RISC-V PC. It doesn't use the usual PC BIOS. It doesn't use the ARM boot mechanism. It uses its own boot process. starting with OpenSBI, which is the firmware interface akin to UEFI on x86 machines. It provides a low-level machine interface for the operating system to give some abstractions to the operating system, so we can take a generic operating system and run it on a specific piece of hardware. So very much like UEFI, there's a bunch of effectively low-level calls. On the RISC-V platform, we actually have 3 security or privilege levels: M mode, S mode, and U mode. And M mode is the machine mode, which is where OpenSBI runs. And then above that is a lower level privilege called S mode, and that's where Linux runs. So it's called, we use M for machine mode, S for system mode, and U for user mode. On top of OpenSBI, and we run Uboot, and we actually have 2 different versions of Uboot: the Uboot SPL for the simple program loader, and then full Uboot to actually boot a real kernel. And then on top of that, of course, Linux runs after that. So right now, I wanted to talk about the software that we've gotten running for this device. The Uboot that we're running on the device right now is based on the version from October, so you can tell it's fairly new code. The patches that we've got making it run on this board basically take the existing FU 540 code from the Unleash board and make some modest changes to support the new processor. On the board, we actually have a little I2 EEPROM, a tiny little EEPROM that holds the serial number, and it can hold a MAC address, and it holds a bit of other information about the board. And so that way we can customize the board and provide some of those serial numbers in a fairly easy to program fashion. And so that EEPROM gets programmed during hardware development. The EEPROM on the board that I have here is not actually programmed, so I'll be actually experimenting with how to program that in the coming days, which should be fun. There are patches in progress to add PCIe and USB support to the Uboot image that we're using. Right now, the Uboot image that I have can only boot off of the SD card, which means that you have to have an SD card inserted in the machine, which is how I'm booting it today. But we're hoping to get the patches for PCIe and USB support finished up and integrated so that I'll actually be able to boot directly from the M.2 NVMe drive that I have installed in the board. So that's a little more work to be done in Uboot. Okay, OpenSBI. OpenSBI, we're using essentially the same version of OpenSBI that we had on the FU 540. We've added a couple of new entry points, and these allow you to get some of this hardware-specific information about the underlying chip, the vendor ID, architecture ID, and implementation ID. And we're going to use those up in the Linux space, so you'll see in a few minutes, to be able to do some patching of the Linux kernel for whatever chip errata you might have. Every chip, as you know, comes out with things that don't work the way that you expected them to, and it's often easy to patch those in software. We didn't want to make the kernel always run with the support for this particular chip. And so there's a new Linux errata mechanism, and the way that we key which fixes to put into the kernel is based upon these new OpenSBI entry points. They get some chip-specific information, which is pretty nice. Let's see. Up in Linux, the patches that we have right now, there's not very many. I think there's 20 or 25 patches. Most of those are actually patching various device tree bits. We're extending some existing drivers that I'll talk about. We're working around the implementation quirks in the chip with the new errata mechanism. The Linux that I'm running right now is currently based on 5.10.9. Some of the patches for this chip are already in 5.11, and some of the patches will be going into the 5.12 merge window, and probably some after that as well. Obviously, we'll be making all of these available when we get the boards published. Right now, we're kind of still tweaking them and getting them working internally to make sure we publish some useful code. Okay, the PCIe driver. This is kind of the new big piece of hardware for the Unmatched processor. It's based on some designware IP. and that driver is already in the Linux kernel. And so getting support for this particular chip is a matter of gluing the way that the designware IP was put into the processor into that existing designware driver. So it's a fairly small patch. The driver is really not quite ready for upstream. We're still restructuring it. It's got some kind of target specific kludges in it that they get it hooked into the Perky clock and reset code. So we're going to be cleaning those up and making those available and getting ready to push those upstream. As I said, it's based on the existing DWC driver for the designware PCIe controller. And so there's no real significant changes other than figuring out which pins the various parts of the designware IP are connected to the processor inside the chip. Device tree. Device tree is kind of an adventure. Everybody wants to have a device tree binary blob in their particular piece of software. So we have 3 pieces of software that all have device tree integrated into them. And it should be the same blob everywhere except where it's not. OpenSBI has a copy of the device tree stuff. In the image on the SD card that Uboot reads, there's another copy of the same device tree binary blobs. And then the Linux kernel has that. And as a result, in each of these projects, you see patches to the device tree as we tweak and adjust the device tree bindings. For those of you who are unfamiliar with device tree, it's a way of describing the hardware in the system to the operating system when it starts up. A lot of the ways in early DOS days, we used to have to hand edit configuration files to tell the operating system where our devices were. And then we got PCIe buses, and PCIe is a self-describing bus. That means when you plug in a device to PCIe or PCI or PCIe, the operating system can actually see that device is there and know what kind of device it is and find the appropriate driver using IDs and all that kind of stuff and the PCIe config space. With microcontrollers and for peripherals that aren't connected via a discoverable bus, you need some way of telling the system where those devices are and how to communicate with them. And that it tells what addresses the devices are mapped to, it tells what interrupts they're wired up to, it tells what kind of hardware it is, what version it is, the addressing space and capabilities of the device. Basically all the same stuff you would get out of a PCIe config space, but it's provided in a binary blob without requiring any hardware support, which is ideal for systems that have integrated, for all the integrated controllers into a system. So for instance, on your PC, on your regular x86 PC, that we use a system called ACPI, which provides a similar kind of information. But as a result, we have device tree blobs everywhere, and we end up trying to keep them in sync to make sure that everybody has the information they need. It's useful to realize that OpenSBI actually tells Uboot that it has a device tree, and Uboot tells the kernel that it has device tree information. And so you can, the higher level device trees end up being fallbacks for that lower level information. Okay, we also had to update the clock driver. Really not very much, not a big change here. There's an existing FU540 clock driver. What used to be called Clock SiFive PRCI FU540, and now it's just called Clock SiFive PRCI. And PRCI stands for Power Reset and Clock Interface. We pronounce that Perky. So if you ever hear somebody talking about Perky, you'll know that it's the kind of the low-level initialization bits of the chip, the power reset and clock interface stuff. We added some hooks to the driver so that each SoC can now have different functionality in the driver, and there are some modest changes in the clock driver, but really nothing big. The biggest part was changing the driver so that it could be modified on a per chip basis. The L2 cache controller, most of what is in the L2 cache controller is actually finding out when there are errors in the memory subsystem. So the level 2 cache controller is what's connected to the DRAM, and it gets to find out about all the errors in the DRAM system. So it's responsible for reporting those errors into the processor. The old FU540 level 2 cache controller had 3 interrupt sources, and the FU740 L2 cache controller has 4 interrupt sources. They added another kind of interrupt source for uncorrectable directory failure. And I have to admit, I don't even know what that means. The driver now uses device tree information to figure out what the capabilities of the device are. So now we've taken this thing which was hard coded to only support the FU540, and we're taking advantage of this hardware description language in device tree to customize this driver based upon the functionality in the hardware. We have a new bus error unit. So if you have is particularly useful when you add complicated buses like PCIe, so that we can actually report errors from the underlying buses up into the operating system and tell us about what's going on there. It's just a new driver. It reports errors. It's not that exciting. The big change that we've added here is the ability to plug in per product fixes into the kernel. It's very similar to mechanisms that exist for ARM64 and x86. It allows you to actually patch the binary of the kernel at boot time, depending upon what the kind of quirks in your hardware are. And as I said earlier, OpenSBI now has interfaces to let us query this information so we can find out what precise chip we're running on from the underlying firmware. And so we're taking advantage of that to plug in some quirks. And there is one quirk necessary, obviously, for the FU740 about some page fault stuff. And so there's a little tiny patch in the page fault handler that we apply based upon running on an FU740 chip, which is pretty neat. So the nice thing about having this as an errata and not just part of the kernel is it avoids using or executing additional instructions on processors that don't have this particular quirk. And so that's why we put in this complicated errata mechanism so that we wouldn't burden chips that don't need the quirk with the additional instructions. Okay, I'm actually running Debian on this device. I wanted to tell you what I had to do to get Debian running. It was surprisingly easy because I took some shortcuts. The funny thing is, for those of you who've seen me talk at LCA before, I often talk about the Linux desktop and graphics stuff. And I didn't have any trouble with any of Debian running on this box until I tried to start running X, and it just crashed. And I figured, wait a minute, why is X crashing on this? I figured it had to be some architecture specific reason. And it turned out there were 2 bugs, one in the Debian packaging of Mesa, where it wasn't actually building the drivers for the RX 580 for the RISC-V processor. And that was just a build configuration issue for the Debian package. That patch was submitted and has been merged. But the other more curious thing was my window manager was crashing as soon as I tried to launch a session. And I was kind of worried that there would be some low-level RISC-V specific problem of running 3D graphics on the board. And so I went digging and found what I thought was a serious problem with the RISC-V support for in Mesa. And I submitted a patch, and the author of that particular package said, no. The RISC-V support is fine. It's Mesa that's broken, and I couldn't quite figure out how Mesa could be broken in this particular way because it would affect everybody using Mesa. But it turned out that Mesa had been recently broken, and I was one of the first to discover it, and so I submitted fixed Mesa and submitted a patch upstream. That's been merged into Mesa, and I'll probably submit a bug fix to Debian because it will, as soon as people start using the Debian package that contains that version of Mesa, they'll start having trouble with the XFCE desktop. So that's what I've gotten running. I haven't tried to build a lot of other applications yet on Debian. Debian obviously has a huge amount of software packaged in main, but there are still some big gaps. There's a lot of packages that aren't part of the Debian ports effort. And so in particular, I don't have a functioning web browser on Debian yet. LibreOffice isn't available. And so there's a huge amount of kind of fun porting and packaging work to be done, left for us to be done on Debian. And so I'm looking forward to getting to play with that and seeing how much of that can be made happen. Until this board existed, essentially all of the Debian porting effort has been done under QEMU. And so this board is kind of an opportunity for us to get away from emulation-based software development and get to native software development. So I was able to do all of the Mesa packaging work and the Mesa bug fixing work running software directly on a RISC-V processor, which felt really, really good. Finally kind of a real computer to use to run Debian on. Here's more information about the hardware. For those of you who, for whom this is the first time you've heard of the Unmatched board, we actually have a crowdfunding campaign going on at CrowdSupply, where you can pre-order boards. Mauser's letting you pre-order boards. There's more information on the SiFive website about the board. And it's a pretty exciting time. Boards are supposed to be shipping soon. We've been kind of finalizing the hardware, tweaking the functionality. One of the recent changes we made was to bump the memory from 8 gigabytes to 16 gigabytes. And of course, changing the memory configuration on the board is causing us to reevaluate all the DDR timing information and requalifying a bunch of stuff. So that's taking some time. But I think in the end, having twice as much memory will be well worth the short delay. And I think with that, I wanted to actually give you a demo of the board actually running, because that's kind of cool. So I have here a console. I wanted to show you the text that the console puts out. It puts out this lovely ASCII graphics logo telling you that it's running OpenSBI and what platform it's running on. And you can see here that the platform actually says SiFive Freedom U540, which is not true. It's a SiFive Freedom U740. More stuff to fix. Who knew? And then you can see down here, it talks about the MMC controller. Note that it doesn't yet talk to the PCIe controller from Uboot, because if it did, you would see that listed here, which would be kind of nice. I've typed in the commands necessary to boot Debian off of the NVMe drive, and it's all set up to go. So I should just be able to hit return, and we should see it starting to boot up. And you can see it's loading the kernel. It's loading, and now it's running this is running the kernel custom compiled for this board. This is not the Debian kernel. The shortcut that I took was to use the kernel that we've been using for internal development and not try to get a custom kernel running. And you can see it's up and running already. So that was booting all the way to multi-user Linux in just a few seconds. If you boot the Linux that's on the SD card, it's quite a bit slower. So it really does show the advantage of having the NVMe drive sitting there, which is kind of nice. Now I should be able to is it running? Oh, there we go. It finally discovered that I had a PCI device connected, and it has the console wired up. So now I can actually switch over to the HDMI input, and you can see the fact that it has the console there. And now I'm going to launch our little display manager, LightDM, and the screen goes black, and we have the familiar cursor, and we should see a login window here. And I need to debug why the keyboard is particularly slow at the LightDM prompt, where it works fine once you're logged in. So this is running the Debian unstable version, of course. I built the image using instructions that are in the Debian wiki for building an image to run QEMU with. And then I just took that same image and stuck it on the NVMe drive and booted right to that. So that it seems to work pretty well. I had to make a bunch of modifications to the installation. I have those instructions, a long list of those instructions for getting a Debian image kind of tuned up. But the good news was I could just take the Debian image that was created from the Debian wiki, stick it on the NVMe device, and boot right up. And after that, I was running native Debian. And then I can obviously run some fun games and show you that the fact that you have PCIe means you have kind of the traditional Debian games available to you, and they work just fine. So this is not low speed graphics. You're not going to see the actual performance, of course, but the frame rate right now is let's see, you should be able to get the frame rate displayed. Yeah, it's 43 frames per second, so it's running basically full speed, which is pretty awesome. So let's see, other things that I can run. Oh, I can show you some information about the system. I remember I was going to do that. Yeah. You'll note that this is a quad-core processor. Let me get that a little bigger. Oops. How do I make that bigger here? There we go. Just took its own sweet time. So you can note that it has 4 cores. They're all RV64 IMA FDC cores. This chip has a 39-bit MMU in it. So we're running in SV39 mode. That means that it can access a maximum of 39 bits of address space. The IMAC FDC tells you all the capabilities of the processor. RISC has kind of a combinatorial explosion of possible processor functionality. It has the integer core, it has multiply, it has atomics, it has floating point and double precision, and it supports compressed instructions. That actually kind of all gets compacted into something called RV64GC, because the IMA-FD is abbreviated G often. So if you see people talking about RV64GC, that's just basically a processor which is designed to run Linux, and it has all the capabilities you'd expect from a processor functional for multi-user high-end operating system stuff. And with that, I have come to the end of my time. And I think if there are some questions from the audience, we certainly have time for those. What is my favorite use case for the SiFive RISC-V chip? Well, we make a lot of chips. For the FU740, this brand new chip in the Unmatched, my favorite use case right now is going to be actually developing software for Debian, getting the Debian distribution running really well in the RISC-V, and being able to actually use RISC-V based PC for work at home. I'm really looking forward to having kind of a full functional RISC-V PC to use at home. So that's definitely what I'm looking forward to here. We also have little embedded microcontrollers like our HiFive, the board that is being sold through the BBC. Can't even remember the name of that one now. That is being that they're going into the educational markets with. So it's going to be fun to see kids learning how to program using RISC-V processors in that environment. Other than that, it's a general purpose computer, so it's going to be pretty exciting. Question: why would somebody choose a RISC-V processor rather than another? The RISC-V architecture is an open architecture, and that's really the key advantage here. There are no licensing fees. You can take the architecture spec and go implement a processor using it without paying anybody or asking anybody permission. And so there are a lot of companies out there exploring what you can do with this processor and taking it in some pretty interesting ways, which is kind of the neat part. It's kind of we have free software. We have some free hardware designs from various microcontrollers up to desktop PCs running with ARM processors. But RISC-V really is the first time we have an architecture that is free enough for us to build our own processors. Next question. When can we have a laptop without the ARM, AMD, or Intel tax? Well, that's going to just be a further development of the RISC-V processors to the point where they're ready to be put into a laptop. You can see that this processor is ready to be used in a modest desktop environment. We're taking advantage of having a PCIe bus to get to the graphics system. So getting into a laptop form factor, we're going to need to do the usual selection of power management, integrated GPUs, other integrated devices, and then the long slog to making it robust and reliable enough for people to use in a laptop form factor. Question from Allison: is that TPM? I assume TPM, the security chips. This board does not have a TPM on it. Obviously, it has a GPIO header with a bunch of pins on it. I'm pretty sure you could plug a TPM into it and access it from that, but there is not one integrated into the board. Another question: is there any capability to use RAM sticks on this chip? This board does not have a DIMM slot. It is using regular DDR4 memory, and so you could definitely take the same chip and put put it onto a board that had a DIMM slot and plug regular memory in. But to save money on this design and to make it a little more robust and reliable, we're soldering the chips onto the board for this release. It's just from a manufacturing and development perspective, it's a lot easier than trying to test a huge range of DIMMs plugged into the board. Okay, a question from CyRevolt. Do you prefer Uboot with OpenSBI, UEFI, or coreboot? That's a complicated question. The OpenSBI is a pretty interesting, a pretty good specification for how you abstract the RISC-V processor away from the operating system. So from my perspective, that's a lot like the BIOS or UEFI. It's a lot simpler than UEFI because it's very RISC-V target specific. If I were building a more sophisticated, larger system, I might be interested in targeting something with a little broader compatibility like ACPI and UEFI for such a system. But for kind of our first PC, it's a lot easier for us to get a simpler software stack running, and OpenSBI and Uboot are certainly a lot simpler software stack. Uboot really isn't relevant for the Linux environment. Uboot's job really ends once Linux is loaded. And so in the Linux environment, you're really talking about OpenSBI and device tree instead of UEFI and ACPI. And I think they have very complementary functionality for smaller systems where you're trying to be able to fix the stack more rapidly and want to have a simpler environment for development. OpenSBI, Uboot, and device tree have some tremendous advantages. We're seeing in the ARM market, larger systems are starting to move towards UEFI and ACPI as they're looking for that kind of that much broader API. UEFI is really effectively an operating system that runs under your processor, and OpenSBI is a much lighter weight version of that. Let's see. Is there a concern that there will not be a single RISC-V configuration to target? That is a realistic concern in the embedded market, where people are very sensitive to cost and are trying to cut out functionality they might not need from their processor. But we're seeing a lot of coalescence around a couple of pretty common RISC-V configurations now. So in the embedded market, you usually see RB32 IMAC devices, and that's a really common target. And in the Linux space, we really are focusing on the RB64 GC set. We're obviously going to offer processors with enhanced capabilities, but the nice thing about having a GC baseline is that you'll be able to get the kernel booted, and then the additional enhancements will be able to be accessible from the kernel or from user space, but you won't have to have them. So yes, RISC-V is probably more configurable than I would have considered, feasible a few years ago. But the fact that we have these baseline standards means that we're going to be able to build software that runs pretty reliably across a wide variety of systems, especially at the Linux level. I'm the maintainer of the Debian GCC packages for embedded RISC-V, and we build a lot of different variants. But the number of variants that we've seen in actual hardware is much, much smaller than that. It just doesn't make a lot of sense. Let's see. How open is the Unmatched? We're trying to make the system as open as we can practically afford to. The design of the processor, while the architecture, the RISC-V architecture is open, the FU740 processor design is not open. There's a lot of IP that we've incorporated from other vendors, like our designware PCIe, that is not our IP, so we couldn't open that even if we wanted to. And so we really can't open the processor specification at that level. Obviously, all of the software running on the entire board all of it is free software. There's no proprietary software on the board in the main software stack at all. I was about to say there's none on the board, but I discovered last week that the USB hub that is on the board to give us 4 USB ports instead of just 2 USB ports actually has firmware in the chip, and that is not free software. It's a USB hub on the board. But in terms of the main processor, that's all running free software all the way down. So the Uboot, the OpenSBI, and Linux are all free software. Let's see. The docs being forbidden to re-upload, I think the docs are probably copyright and are not free, are not under a CC license, which makes sense from a proprietary hardware company. Let's see. Likely to see production on the level of what Micromagic allegedly achieved. I haven't looked at that board very closely, and so I'm not entirely familiar with what it's doing. But again, this board is targeting a very different level. This board is really trying to create a board that you can do native Linux development on. It's not a micro. It's when Limor was talking in the keynote about the 3 levels of computing, this is the highest level of computing. So it's a machine you could legitimately run a desktop on. Last of the questions. Intending to create a de facto standard user desktop platform. I don't think so. This is a mini ITX board. We haven't created any standards here at all. This is using standard PC components. The goal here is to get a board that you can do native RISC-V development on Linux out to the community and to make it as widely available and easy to access as possible. And with that, I want to thank you for your time today. And I hope to see you all again at a LCA in the future.
Thank you so much, Keith. That was really fantastic. And we managed to get a lot of excellent questions in. And for everyone, we'll just go into the room changeover now. And we'll be back in 10 minutes with the next talk. Thank you so much, Keith. See you later.
Thank you, Pia.